Good afternoon, everyone. My name is Wan-Jui. So I'm an AI researcher at Dutch Railways. So I used to work in the Department of Maintenance Development, mainly working on predictive maintenance. But then we start to see the necessity to starting further in the logistic arrangements for the maintenance. So I switched to the R&D hub logistics since this year. But if you are interested in how we progress in predictive maintenance at Dutch Railways, I have two colleagues. They are also in this event. They're from the maintenance development. So feel free to contact them if you are interested in our development. So I mainly working on the AI techniques that try to solve the maintenance of the trains from all the different perspectives. But in here, this talk, I will mainly focusing on one technique that we're using to try to solve the shunting problem. So I think from the presentation of Michelle, especially on this answer to the last question, we know that for the maintenance of the trains is usually on the short fixed time slot, and we have to get all the train materials and also the crew. They are really there at the right time. So I think predictive maintenance is important. They can try to predict the failure, but afterwards, how to react to it quickly, how to make a planning and scheduling according to the really failure of the trains, how to make a good plan of that, to make good use of time is also very essential. So that will be the focus of this talk. It's about the scheduling and planning, but not really about the predictive maintenance. So at Dutch Railways, we have about 800 trains. It's a small country, so it's actually a pretty big fleet for such a small country, and we have a very dense network. Still expected to grow in the upcoming 10 years. So we are going to have more trains. And when these trains are not carrying the passengers during the traveling hours, they are going to the shunting yards. There they will get maintenance carry out, or they will just get parked there. So basically, we don't allow trains to park at the stations when they are not carrying passengers. They have to go to a shunting yard and go right over there. So there are about 35 shunting yards we have in the Netherlands. So this is one of the smallest yards we have. It's called the Kleinbinnenkost in The Hague. So here you see there are many different types of tracks. On the most right side, you see a blue infrastructure. It's called the washing machine. It's special it's a special machine for washing the outside of the train. And right next to it, it's a gray box. It's for the internal cleaning of the trains. So you see that some tracks has special functionalities. So trains that comes into this yard in the night and get cleaning or gets inspection, and then they have to wait until the next morning so they can carry out again the passenger services. But of course, there are more trains than that, and it's interesting to know actually what's the capacity of a specific yard. So my department is trying to figure out actually in a specific yard what is the maximum capacity. So we have many different simulation softwares. One of them is one is them for the capacity analyzer. They try to generate different shunting plans for a specific yard, and then based on that, we'll try to find solutions. And if 95% of the situations that we can find a solution, then we will keep on upgrading the capacity, and then get up to the next level to see whether we can increase it, to see whether we can find the maximum capacity based on this step-by-step analysis. So this is an example of the shunting instance that we generated from our simulation software. On the left side, you will see the time of the incoming trains and which composition they have, what kind of task they have to be carried out, and which track that comes in. And on the right side, the time they have to leave, and which composition and which track they have to leave. So basically, we'll generate thousands and thousands of these kind of different instances. So this is a planning scenario, and the important thing is to try to find a solution for that. And to find a solution, there are many problems we have to solve. So there are many different sub-problems inside our train unit shunting problem. So on the right side, you will see there are about 7 different types of problems they actually have to solve. And it's not really possible to decompose them, to solve them separately. It's really important to solve them as a whole. Then you can really get the optimal solution. If you try to decompose the problem, there's no guarantee for the optimal solution. So in the end, it gets a very complex problem and very difficult to solve. But anyway, we have tried to study some techniques to try to solve the problem. We have studied some more classical methods based on optimization, and then also based on the heuristic search approaches. And now we are going to the AI approaches. So the good thing is that with this kind of technologies, we can try to solve a planning instance within a few minutes, when people can only solve one instance with almost 24 hours. So it really reduces a lot of time for the planners to find a plan with the help of the computers. And we are also right now at the stage try to put this into the operation. We have started up a project half a year ago, and now it's in implementation process. So here you will see this is how a planning solution looks like. So we have just see a planning instance, there's a scenario, and this is how the computer tries to find a plan by itself. I'll just play it again. So you will see the trains are trying to move around, find this composition, get to the right track to get a task done. And when the time is up, it's going to try to leave the track. So for this instance, it's pretty easy to solve. For the computer, it takes about 2 minutes, but again, it takes a human maybe half a day to solve. So we have already know with these kind of optimization approaches, we can actually solve them. But there comes a next question, because humans, they prefer more consistent plans, and they also like to have some kind of heuristics or some kind of planning policies. And these are the things that's basically lack in the classical or optimization-based approaches, because they are mostly about random search. So you try to search or try to guide the search, but then there's no basic policy, which means you have the same instance, same problem you have to solve, and you can find many different possible solutions. And every time you can find a different solution. And this kind of inconsistency is something that human planners, they don't really like. So that's why we try to explore the machine learning based approaches, because once you build up a machine learning model, it means that you would have a fixed policy there lying inside the model itself. So you can try to interpret the heuristics policy that was embedded in this model. And it's also because that we see the possibility of this research starting from 5 years ago with Google DeepMind. They also try to solve the planning and scheduling problems with machine learning approaches. I think everybody knows the AlphaGo, so they try to solving this kind of strategy, kind of game planning, but then they use the same approach, try to make the planning for the London metro network. So that's why it intrigues us to try to use these kind of approaches to solve our train unit shunting problem as well. So the basic approach they use is the reinforcement learning. So I will shortly describe what it's about. So basically you will have a learning agent, and it will try to interact with the environment. This environment is like a black box to the agent, but this environment will tell the agent once the agent has choose a certain action. So if the agent say, I want to go to the left, the environment is going to tell the agent what is the result once you take the action. So the resulting state and also the reward you will get by taking this action. So by interacting with this environment, agent will try to learn what is a good action to take in able to get more rewards out of it. So the whole learning is about try to interact and explore properly with the environment. So the design of the reinforcement learning is focusing on the state representation design, action design, and the reward design. And we will see a little bit later on how we try to design all these things for our shunting problem. And of course, the agent itself is a machine learning model, and the training of it is also important, but then we don't really focus that much on this presentation. Okay. The planning problem gets more focused these days is because Google DeepMind proposed the deep QLearning in 2015 and suddenly gets more attention about how to solve optimization approaches based on AI techniques, because it's really something rarely studied before, and suddenly it gets more and more interest right now. I think if you go into the recent researches, you will see that, for instance, the driverless cars, they're starting to trying to find the optimal passes using these type of techniques more and more. So one of the most popular reinforcement approach is called the QLearning. So the Q means the accumulated rewards that I want to get, and I want to actually maximize this Q value. So the classical way of QLearning is try to store the Q values in the matrix. So for each state, I'll have different actions. So in my matrix, one dimension will be the state, and the other dimension will be all the possible actions, and I will store all the Q values right over there. But for complex problem, as you can imagine, like our train unit shunting problem, this matrix gets very huge. So it's basically impossible to store things into a matrix anymore. So that's why what Google has do is try to approximate the Q value, use a deep neural network. So basically, you have a neural network model that try to generate the Q values for each action when you're giving a state up to it. So in this way, you don't store the Q table anymore, but you just try to approximate these values. So this is essential information about it, the deep Q network. So here I'll try to explain a little bit, then how do we design actually the environment with all these reward and action and states for our problem. So here we use the example also, the one is described it, the climbing course. This is one of the smallest yard we have. You will see on, there was a get track almost left side, and then you will go to different parking tracks from 2 to 9. And then you can go to cleaning platforms 11 and 12, or you will go to a relocation platform. There is also for external cleaning. So there are many different types of movements, as you can see. There are in total 52 movements actually. So there are actually already many actions taken into account. Is one of the smallest yard that we have. So when you want to try to a larger yard, you will see there actually will be hundreds and hundreds of actions. They are possible given each state. So it's actually very difficult to solve in the end with this kind of architecture. But anyway, I will try to explain a little bit what we are trying to solve. So we have just explained there are many different sub-problems in our problem. And in here, we didn't try to solve everything because it's difficult to solve everything at once. Here, we didn't do the combination and split, for instance, because combination and splitting requires interaction between the trains. And this made the problem more complicated. which means we might need a multi-agent type of algorithm try to solve it. These are much more advanced approaches than our current setting. So here we use the single agent, and we don't try to solve the combination and split problem. And as I have described, it's important to design the state representation, action, and rewards properly, because you want to train this neural network. And this state representation is an input to the neural network. It gives information for the neural network to recognize what is the current situation. So you have to embed sufficient information in it. For instance, we have to embed what is the current state of the yard, which trend on which position, is it currently under cleaning, and what time does it probably has to leave. So all this important information that we think are important for making a plan, then we all need to include in this. And for actions, I have described there actually 52 possible movements, but because we include a service task, which means there's a concept of timing right over there. So you don't always want the trains to move around. So we have an extra waiting action, which means at this current moment of time, if I prefer there was no movement, then I would just choose the wait action. Because there are 53 actions in total, and if you don't choose wait, you're just going to choose a movement, and in the end, you are going to have many movement. And this is also what we don't want to have, because each movement means you have to have the driver, and also it's going to block certain facility. So each movement will have some cost, and we want to minimize this cost as well. Okay. So we have just also mentioned that for our smallest CRD already 53 actions, so it's already pretty big. So what we actually try to do now in the end is, well, I'll skip some slides because I don't have a lot of time, but I think that one of the design for the rewards is, of course, try to make the planes properly found. And for that, you can imagine that finding the plane is letting trains leave on time and also get their tasks carried out. So you will see that a correct departure, you will get a high positive rewards, and also a correct finish of a task will also give a positive rewards. So these are all just logical choices. If you just look at it, you will see there was no strange things inside. And also we try to avoid too many movements. So we try to give the relocation some negative rewards, try to avoid too many unnecessary movements. And of course, when things get wrong, you will get a violation. For instance, my track is already full, but then you still want to try to insert a train there, that will cause a violation, which means that the model shouldn't try to learn that at all. It's just try to avoid doing that. And there are many different types of violations. So these are just a few examples right over here. For instance, choosing the wrong time for departure, or choosing the wrong type of train for departure, or try to depart a train that is not properly cleaned. So these are the violations. So as I have explained that there are many different actions, and if we try to learn all the actions at one time for one single model, it actually takes longer to converge. And when we try to scale this to a larger yard, we'll see the problem, because that there are hundreds and hundreds of different actions, and it gets very difficult to converge. So we have to think about actually how to try to solve this problem. So we try to transfer the Q network to the value network. So what does it mean? So value network is try to predict the value of a specific state. So we only estimate how good a state is. It doesn't look at action anymore. So which means when I give a state, after I choose a certain action, I would have a resulting state, and I will only evaluate how good this resulting state is. So there is only one output in the end now. So this is the major difference what we do. So we call this the value iteration with post-decision state. You will see on the left is the old structure where we try to predict 53 actions at the same time. But now with the new structure, we only try to predict one specific value for a state. So with this new structure, that we try to see actually how it performs. And this is our experimental setting. We try to run different problem instances for different lump of strengths to see how well they progress for different lump of strengths with different approaches. So the neural network we use are rather simple. It's not a very, it's not really a deep neural network. It has only 2 hidden layers. So we have tried to test on the DQN and the value network. So we just explain these 2 approaches separately. And then here you can see the results of them. On the left side, you see the one carry out with the value network. And on the right side is the one with the Q network, which try to learn 53 actions at the same time. You will see that the Q values of the value network are actually higher, which means it try to it try to let more trains depart because most positive rewards gets from departing proper trains. So it actually gets higher value. It means it solves more trains. And also it try to converges slightly faster. And in the end, we try to look at what is actually the performance of the solvability. That we see that also it's actually with the value network, we are able to solve 90% of the cases. But I have to say that with the critical ones, we actually can solve almost 100%. So this kind of machine learning based, especially reinforcement learning based, is not guaranteed to really beat the current state of the art in the optimization based approaches. Okay. So this is just a quick visualization of our reinforcement learning agent. You can see actually how it's trying to learn. On the right side, there were arrival trains. On the left side, there was a departure trains. And at each time you try to make a movement or it tries to wait, and you will get current reward. You will get some rewards or get some punishment. Okay, this is my presentation. I think I'm exactly on the time. Not sure whether there are time for questions now.